Okay, so guys, we are starting now. Hi, good morning. Welcome everyone. So Phi I is pleased to welcome you to this workshop on quantum computing and quantum information. Our speakers, so Dhruva Sambrani from MS18, Aabhas from MS18, Apraman MS20, and Sahil from MS20. So all four people have painstakingly put in curated this very nice workshop. Hope all of you will learn something and will have fun. So let's not waste any more time and let's get started. For the Zoom people, unfortunately, you won't have refreshments, but people in LH3, you will be served something during the first break, hopefully. So, okay. When are we taking the master? Approximately 1 hour. You start. Okay. So, I guess we'll start with the first session now. That is Dhruva's talk.
Just ask it. Yeah.
So, people who have joined online, is the audio fine? And can you see the blackboard?
Yeah.
Yeah. Yeah. Okay. I think I'll start then.
Okay.
You guys can hear me too, right?
Yes.
Zoom. Yeah.
Yes, yes.
Yeah. Yeah. Okay. So today I'll be. You guys can hear me too. Yeah. Okay. So today we'll talk. I mean, this session, the first session of these 4 sessions, is going to be an introduction to basically the math of QM and why physics and computation are intrinsically linked. And I don't mean this in the sense of the way that I have given talks in Turing Club, where I've said that computation is important for physics. I don't mean it that way. I mean that computation and physics are finally, they are the same thing. And therefore, the fact that the innovation, I'll call it, of quantum mechanics led to a new paradigm for computing too is not too surprising. And it goes beyond just computing as in the sake of doing numbers and stuff, but rather it goes to the point where you can study the nature of physics through things like information, which were initially defined for data processing and stuff like that, which were mathematical definitions. And people saw that there was this connection between physics and computation, which has led to insights in both directions, both in the direction of computation and in the direction of physics. So most of the information side of thing is what Aabhas will be taking next tomorrow morning. But the end goal of this workshop effectively is to look at very broadly 3 things that people do in quantum computing, quantum information, whatever that means. So there is one side is the quantum computing, which we would like to talk about more, but we don't really have the time. And also it's not the most fun thing to talk about in a talk like this without people knowing the absolute, you need to be perfect with your quantum mechanics basics. So without that, doesn't really make sense to talk too much about it. We will still, of course, touch upon it. And the second thing is, of course, implementing what your algorithms are on a physical system. And that is what we'll be doing in the evening session. And then tomorrow's session deals with quantum information, which is the study of the mathematical properties of quantum mechanics and how that intrinsically relates to the study of information. It's not very insightful, but that's why I leave it for tomorrow's talk. So first, I'd like to introduce the world as a calculator, or rather as a computer. What is physics? Finally, the physics is the study of some system. You have this particular system and you want to study what happens to the system given certain things. So the first thing that you'll need to do is to define the system in a mathematical formalism. I need to be able to represent it in a way so that I can talk about it. That is not very surprising that we do even with Sorry. Record on this computer, right? Yeah, states. That's not something that's very surprising, because even if I wanted to explain that chair, I would still have to use words to express it. It's just that these words are not very easy to manipulate, because, for example, if I say that the chair is yellow, it's not very clear what yellow means. It is subjective. And therefore, like Aabhas said when we were discussing day before yesterday, the problem with physicists is that we tend to put things into words, and mathematicians have one thing good, is that they tend to put things in numbers where the definitions are absolute. It's not just whether it's clear or not is a personal thing, but they're absolute. You cannot change. There is one definition that everyone works with, and because that definition is known, there is no ambiguity in the words that we are talking about. So first you need to define states, effectively representing the system in a way that is not only captures what we want to study about the system, but also it captures the it also must be easy to manipulate, such that we can do things to the system and see what happens. The second is dynamics, obviously, is how does this, given the state, how does the dynamics of, how does the state interact, rather, what are the equations of state, so that the state moves from one state to another state to another state, and how does this trajectory of states, how can you predict this trajectory of states given the initial state? The third thing is, finally, you have to measure the system, and you have to look at, because finally you want to gain information from the system. So you have to measure the system, and you have to look at the system. And I mean, a lot of physics tends to skip over this measurement as a given, but we'll soon realize why it's not a given. Computation is not very different. Again, you have to first represent your data. Then you need to define the functions which takes you from, in your set of data, it takes you from one instance of the data to the other instance of the data to the other instance. And then the third one is the output, how you finally get the data out from the system. Can I read out everything in the computer? Can I not read out everything in the computer? What can I access, etc. So if you see that these three things are effectively the same in physics and in computers. If a physical system can store states, it can perform dynamics, or if I can control its dynamics, and I can somehow gain information from that system through measurements, then I can also compute. Equivalently, if I have a computer which can do these three things, then it can also act as a physical system which can do these three things. The second direction, where you have a computer which can do calculations, which has a set of states, and then you're moving from one state to another state, that is something we do every day in numerical computing. You have this, there's this Hamiltonian, let me solve this Hamiltonian, diagonalize it. Akshay is writing an entire master thesis on it. So that's something we've been doing for a while in the past, let's say 20 years. But the other way is where you make the system do computations for you. That is also not been too, it's not a very new concept. It has been going on for a while. It's just that now there has been, these two have been intrinsically collected through the insights of the likes of Feynman and von Neumann and Turing, who in their own ways connected these two fields of physics and information theory in such a way that you can see one as an instance of the other. So let's begin with the mathematics for computation, for quantum computation. But before we get into the maths of quantum computation, let's do the classical mechanics. Like we said before, we need to define three things for any physical formalism. The way you are defining your states, the way that you're defining your dynamics, and the way that you're defining your measurements. In classical mechanics, you take a single particle, the simplest system is a single particle, and you have certain real numbers, which we denote as x. So, for example, the simplest particle that you can think of is a particle on a one-dimensional, in a one-dimensional space. And this one-dimensional space, the position of the particle is perfectly determined by one number, which is given some reference point, the distance from that point in the positive or in the negative direction. The second number is you need as its velocity. Given these two things, this tuple of just two numbers, you can determine everything. But the point is that these two numbers that we are looking at, they have to follow certain rules, and these rules make them real numbers. I cannot put other numbers into the position and the velocity, and I have to put only real numbers in this. One could also simplify, one could simplify it further and say that we are in a discrete space, and therefore the only values that I'm allowed are integers. So 0, 1, 2, 3, but you can take one as the limit of the other and stuff like that. But that's not the point. But then second step, so the states over here are just real numbers. So R1, R2, or something like that, where this is the position in the phase space, which is, let's call it phase space. The dynamics is then determined by your system, whatever system you have, that doesn't matter, but it's just a function which takes this set of two numbers, two real numbers, to another two real numbers. In time, as I keep stepping it forward and forward, you get different points. For example, if I had a particle which experiences no force, then all my what do you call it? My update rule will be x comma v goes to x plus vt comma v, and that's all. There's nothing else. If I have an acceleration, then my v also changes and x changes and all of that. It's not surprising. It's just that there's this one function f, capital F, which is given by either the Hamiltonian or the Lagrangian or the Newtonian of the system, and you write down some equations, solve it, but we don't really care. Finally, the measurement is kind of given for granted. You say that you can observe both this and this. I can look at the position, I can look at the momentum, and or velocity, whatever. And if generally though you interact your system with some sort of a meter, and what you're measuring is not x and v directly, but rather some function of x and v. And this function, given that I know how m looks like, I can go back and find what actually x is. If I have multiple objects, all I have to do is just repeat these numbers. Then this function will, so I'll have x1, x2, x3, v1, v2, v3, and this function will now depend on x1, x2, x3 if there are any interactions between the particles. It's not very difficult to go from this. With the advent of StatMech and stuff, people started realizing that this is perfect, this works great. It's just that for larger systems, it's a lot harder to deal with this. When you have systems where you don't know the dynamics F properly, that time what happens is you have to deal with probabilistic, these functions which are probabilistic, where you don't know clearly whether it will do this or this. It may go from state 1 to state 2 or to state 3 with some probability. And to represent this kind of system, either where you have incomplete information or when you have many systems, many small systems, many particles which are going through the same dynamics, people came up with ensembles, with the concept of ensembles, where you move your state space from just two numbers to first defining a space where the particles can exist. So for example, going back to your case of the one-dimensional chain, you can define what are the values the position can take. So in this case, it would be all the real numbers on that line. And instead of saying that a particle has one real value, one real number, you say that the ensemble, that is a collection of particles, can have one of these R values with a probability density given by some rho. Or I'll just call it P because I will use rho later. And like I said, I can discretize the space and then call it like a set of tiles where I can stand on either of the tiles. And I can say that the probability distribution is the position or the state of the system is a probability distribution on the space. So what is previously just one number goes to a probability distribution where the position of the probability density of a particle being in that position is given by Pi. And because the particle exists and it must be somewhere, you take the vector, you can write this as a vector. You can write this as a vector, and you can take the sum of Pi equal to 1. As far as it's measurable, but so now we have jumped from just single numbers to vectors of numbers, where the vector is a n-dimensional vector. That means I have n real numbers, and the representation of each of these numbers tells me that in this ensemble, P fraction of the particles are in node I. Pi fraction of particles are on node I, and because all my particles have to be somewhere, I can sum up over all of them and get it as 1. Now, the interesting thing about this kind of formalism is I can do this. Okay. I can do this. I can take. Okay, I'll write it and then I'll move. But suppose P1 is. Suppose P1. This is not P to the power 1, it's just P1. Is a vector, is a probability vector. And P2 is another probability vector. You will see that I can take C1, P1 plus C2, P2, and C1 plus C2 is equal to 1. I can take this and this will still be a probability vector, because the only thing that I have said that probability vectors need to have, okay, and another thing, Pi is greater than 0. Probabilities have to be greater than 0, and that's something I missed, I'm sorry. But you say that C1 and also C1 greater than 0, C2 greater than 0, right? So if I take a probability vector P1 and P2, two probability vectors P1 and P2, multiply them with real numbers C1 and C2 such that C1 plus C2 is 1 and C1 is greater than 0 and C2 is greater than 0, then I can show that the resulting probability vector is still the resulting vector is still a probability vector. Why? Because you can do it. You can take C1 times. So if I take a sum over all the elements, you will see that the C1, you can clearly remove out C1 times P1 plus P2 plus P3 and stuff, which takes it to 1, and C2 times that, which takes it to C2, and then C1 plus C2 is 1. We know that. So therefore, this is still a probability. What does this mean physically? If I take an ensemble, then I take 30% of I create a new ensemble from two old ensembles. I take 30% of the particles from here, 70% of the particles from here. My resulting, whatever that is still an ensemble. And my state representation allows me to represent a mixture of different ensembles, and I can still work with it. I can still work with this system. Does that make sense? Any questions?
I don't understand how you went from P1, P2 to ensembles later. I don't know how that.
Yeah, sure. So, for example, let me take a put. Okay, sure. So, for the Zoom guys, Arhan asked, what does C1, P1 plus C2, P2, how does it relate to the physical scenario of ensembles? P1 and P2 are the states or the representations of two ensembles, 1 and 2, suppose. And C1, let's say, is 0.3. C2 is, let's say, 0.7. I can take that because C1 plus C2 is 1. Effectively, what I'm saying is that I'm taking 0.3, that is 30% of P1 and 70% of P2, making them all together. And
I didn't get that. Could you try again?
How do I turn it off?
I'm sorry. I'm afraid I can't do that.
Sorry. Yeah, so C1 is 0.3 and C2 is 0.7. It is effectively that I'm creating a new ensemble, P3, let's call it. P3 is equal to C1 P1 plus C2 P2. Does that make sense?
C1 is a real number.
C1 is a real number.
How is that randomly sampling?
I am not randomly sampling anything. I'm just saying that I'm not sampling anything. I'm saying that let me create, in quote unquote, create an ensemble. I'm not actually physically sampling anything. I'm just saying I take 30% of P1, 70% of P2. I'm not taking 30 and 70. I'm taking 30% and 70%. So there's no issue of sampling here. There are still infinite particles. I take 30% of an infinite particles, which is still infinite particles. So this in mathematical jargon is that the probability vectors form a vector space over convex combination over real numbers, which means I can take any real numbers and I can add them up like this. Convex combination simply means that the C1 plus C2 must sum up to 1. And this allows me to create new states, which are still within the framework of whatever we're talking about. Then we can also define something of an inner product, which is if I take P1 and P2, again, two different ensembles, and let's say that it's discrete ensembles, which means that I can do this kind of business. Then I take P1I, multiply it with P2I, which is I'm taking the, again, these are not to the power 1 and square. Please don't take them that way. But so it's P1I times P2I, and then I sum it over this. What I'm doing is I'm taking two vectors, multiplying both of them element wise, then adding it up. That's all I'm doing. Now this value will be a number from 0 to 1. You can check where it is 0 when, for if let's say that I have two ensembles such that one ensemble, let's say ensemble 1 is only on node 1 and ensemble 2 is only on node 2. Then what happens is if you simply multiply it out, you will see that it will always be 0. And when I add up all these 0 numbers, I'll still get 0. So the only way that this sum can go to 0 is if all the elements are 0, because all these are positive numbers. So effectively what we are saying is that these two are separate. There are no two particles which exist on the same node from ensemble 1 and ensemble 2. Whereas the other case where it is 1, you will also see that this only works out when P1 is equal to P2. And in that case, what we are saying is that these two ensembles are the same ensemble. So I can talk about how similar two ensembles are and how different two ensembles are. And effectively what we are looking at is the overlap between these two. Of course, in the more continuous case, this sum becomes an integral, this becomes a product, you put a dx, sorry. Now we have talked about states, very good. What dynamics are allowed? So you see the previous case, what he said is that you can only take real numbers to real numbers. It can't go out of the state space. I can't apply a dynamics onto a system and suddenly get something new which is not the same system. The system must still be representable by the same method, which means that if I take some t which is some dynamics, then T times P must still belong to the set of all probability vectors. That should be obvious, because if I take an ensemble, do something to it, it is still an ensemble. And because it is still an ensemble, and because I've said that I can represent every ensemble with this kind of formalism, then T must follow certain rules such that it retains the structure of P. These matrices, again, if you take them the discrete way, are column stochastic matrices. They are n cross n matrices. So let's say that I goes from 0 to n or 1 to n. Then you have an n cross n matrices, which are 1, 2, 3, 4. This has a size n, and this also has size n. But I can't pick any random matrices. I have to pick only matrices such that their columns sum up to 1. That is, if I take the sum along this has to be equal to 1. Sum along this must be equal to 1, and so on until for all the columns. The rows need not be. Why do we want this? Let's take a multiplication with some vectors here. I take P1, P2, P3, and I know that this is a probability vector, which means that this sums up to 1. We know that. And if this does not sum up to 1, when I multiply this with this, when I multiply this column, this row with this column, you see that this first element multiplies with this. Similarly, the second element multiplies with this, the first element. The first element on the second row multiplies with the first, and so on. So you have the first column multiplying with the first one, the second column multiplying with the second one, and so on and so forth for all the vectors over here. When I take this sum of all the elements over here, you can factor out, like you can rearrange terms so that you see that it is basically, you will get something along the lines of the length of this vector, not the length, the values of these vectors. So let this be T1, T2, so on. So you have T11 times this one, which is 1, plus T22 times the length times the sum of this vector, which is 1, and so on. What is my, yeah, T12, which is this element times 1, and so on, which must be equal to 1. So what happens then is that I am constraining that the columns sum to 1. And how do I apply this dynamics? All I'm saying is I take this row stochastic matrix and an n cross n matrix, multiply it with a n length vector. That's not very difficult to do. I'm not going to do that. Finally, so this is row stochastic. I'm not going to write it because it's there on the slides. I'm sorry. Then finally, you want to, the next question is of observation. Now, the observation can be of two ways. One is where you can literally observe every particle of the ensemble, where I can see everything. I can see each particle, and then I can, this effectively is what you call sampling, where you sample particles from the ensemble and say, oh, where is this position? Where is that position? And effectively, all you're doing is you're sampling from this probability distribution, and you're saying that, okay, with the probability of something, I'm getting 1, with the probability of something, I'm getting 2, so on and so forth, 3, 4, 5, 6, minus 1, minus 2, minus 3. And you'll say that, yes, this is, this probability distribution is what I want to observe. That is the measurement of the system. But more often, you don't really have that kind of control over the ensemble. Instead, you just have another meter which interacts with the ensemble, and it gives you a function which takes a probability vector and gives you some expectation value of types. That's why I've taken an M average, where instead of giving you a value M for one particle, because you have an ensemble, it gives you the average value for M. So people who have done CHM 102, you'll see how all of this is very closely similar to what you would have done in CHM 102. It's just that I've not put it in those words. But the main difference is that I am only allowing real numbers. Now let's come to quantum mechanics. So, like I said before, I said, oh, I'm only allowing real numbers over here. Let me drop the real numbers. Take an upgrade to which gets under erasing this, I'm sorry. Again, we go through the same business. There's one small caveat is that previously in the probability distributions, we assumed an ensemble of particles. It's not one particle, it's a group of particles which are working together. Now what we have is we go back to the single particle regime. We say that there's a single particle. And just like how we had taken over here a vector, we again take a vector. We'll call them like how I call P1, P2, whatever. I will now call it C1 and I'll put something like this. Wait, instead of doing that, I will. This is what I write my state as. What does this mean? We still don't know. We've still not talked about that yet. I'm just saying that I can represent my state like this. Now I will give it meaning and I say that C1, C2, C3, that is Ci, it belongs to the complex numbers. It does not belong to the real numbers anymore. I mean, it belongs to the complex numbers, which means it can be real, but it is also complex. Can also be complex. And this 1, 2, 3 that I have written in this weird kind of a bracket, it's called the ket notation, is, and these are called kets, is that effectively that the state, quote unquote, is in 1. That is, the particle is in quote unquote 1. And similarly 2, 3, and so on. But now what we say is that, like before, I said that P1, P2, P3, this sum up to 1. But in this case, I don't say that because they're complex numbers, I can add it up, sure. But I don't say that this number sum up to 1. I say that I first take mod of the number, square the number, sum it over all I say this is equal to 1. Effectively, what I'm saying is that there is still some constraint. I can't take 3 n random complex numbers and put them all and say that, yeah, this is a quantum state. No, I am saying that there still is there's still a constraint over the complex numbers. And the constraint is this, that their mod square must be equal to 1. Again, you can see that if I take let's say I take, and I'll generally be using things like, previously I was using P, now I'll use psi. Let me take psi1 is one such vector. Psi2 is another such vector. So then I can do the same business where I had previously taken 2 ensembles, picked some things up and done that. Where instead of taking real numbers, I'll take complex numbers. So then if I take such a combination, then you will see that C1, okay, there's a, okay, I'll just call these D, just for the sake. Yeah. So I take them with D1 times this, where D1, D2 belong to complex numbers, and D1 plus D2 mod squares is equal to 1. I say that if I take 2 quantum states, do this kind of addition where I take 2 real numbers, 2 complex numbers, scale it up such that the complex numbers are still constrained by this kind of a sum, then you will get back another complex number. Again, I'll leave that for you to prove. It's not too difficult. It's just literally opening up everything. just open up this, multiply it with D1 everywhere, open up this, multiply with D1 everywhere, add them element twice, and then take the mods of them, square it up. Then you say that unless this condition holds, this is not a state, or if this is a state, then they are an if and only if. Now, similar to the last time, how I talked about how similar to probability distributions are, I can also look at how similar to quantum states are. At this point, I've introduced quantum states in a very ad hoc manner. I've not told you how to interpret these things yet. I'm just saying, let me define a state which looks like this. I will also define the dynamics of it, but let me define a state like this over such constraints. When I do that, I am allowed to do certain other things, and I can do something known as an inner product, which gives you the overlap. If I have such a state, whatever state, I can take, suppose I have psi1 and psi2 again. Psi1 is the get, psi2 is the get. Then I can define, and then I can define an inner product, which I'll just represent by this. I'll define this inner product as equal to C1, which is basically the first component of the psi1 vector.
What is psi1 and psi2 representing?
Psi1 and psi2 are two states of the quantum system. I've still not still told you how to think of these. Think of them currently as just a vector of complex numbers. Previously, we looked at an ensemble where you had a probability distribution and we call that a vector of real numbers. Now I'll say, what can I do with the complex numbers? Have I still told you how to interpret them? No, I've not yet told you how to interpret them. I will tell you how to interpret them when you come to measurements.
Okay.
Yeah. Naturally, this is a very rushed job because 2 hours, and I'm skipping over a lot of important things. For example, what about the inner product between 1 and 2, which I conveniently ignored. So I say that it is C1 star C2. Sorry. Okay, let me represent these with C and let me represent these with D. So I'll call these with C. It's a. This is D. Then I'll take C1 star D1 plus C2 star D2 plus dot dot dot. It's the same thing that I take the sum over. And to represent it more simply, I'll just call it sum over I Ci star Di. This is what I call the overlap between these two. Now again, it is this time it's a lot harder to show it, but this number is also going to lie between 0 to 1 for normalized states. Where if psi1 is equal to psi2, then it will be 1. If psi1 and psi2 are what we call orthogonal, something that you might have done in math 101, then you'll get them to be 0. I will again leave that for you to read. Now we've dealt with the states, which have already taken up the entire board. This state. Yeah. Right. So we have the states which are defined as column vectors, and Now we want to talk about what operations are we allowed to do. So again, you see that this is a vector, which means that some kind of a matrix is what we want. But if I take first thing, the obvious thing is that over here, the column stochastic matrices can only be real numbers. You can only have real numbers over there. But in this case, you're again allowed to have complex numbers. So now the question arises saying that can every matrix of complex n cross n matrix of complex numbers be used? And you say no, you can't use that, because you still need to make sure that the overlap of psi1 with psi1 itself must be 1. I still need that. I cannot say that psi1 after doing something is no longer the same as psi1 itself. So again, slightly shady, but allow me. So we define what we take as unitary matrices. And unitary matrices are matrices such that U dagger U equal to U dagger equal to identity. What is U dagger? U dagger is simply you take an element wise conjugate and then you just transpose it. This is what is called U dagger. Again, it's just a matrix. And you multiply these two. If you get an identity, then it is allowed. Again, the understanding of this we will come to later. Now we come to measurements effectively, and how we actually think of these states that are taken as psi1, psi2, etc. With that, let me take a particular kind of matrix. I have introduced new notation here, which I probably shouldn't have. So we said this precludes the other way around. It's not vector. Check. Yeah. So now let me take another the same state. You could see right. Let me take this and let me take a matrix, this kind of unitary matrix, which is going to have 0. Let's say that it's a 4-dimensional thing. So this is from 1, I goes from 1 to 4, and it is 0, 0, 1, 0, 0 everywhere, 0 everywhere. Right? I take this specific matrix. Now, this specific matrix, let's first set that it is U dagger is identity. Yes, let's check that U dagger is identity. U dagger is simply taking a transpose, but this is a symmetric matrix. So taking the transpose leaves it as is. And this is a real matrix. It all has just real numbers. So taking the conjugate leaves it as it is. So effectively, this is equal to U is equal to U dagger. Now let me not sorry. My bad. Yes. Now let me apply this. Okay, let me continue with this. So this is U, which is also equal to U dagger. Now, if I take U dagger and I apply U to psi, that is, I do U times psi. This, first of all, the question is, can I do this? The obvious answer is no, because if I take U into U dagger, I multiply this with itself. That's not identity. That's clear if you do the multiplication. So therefore, can I do this? No, I cannot do this. I cannot do U times psi, because this is not an appropriate dynamic operation. Instead, what I can do is I allow you to do it. And I say that, okay, take this U times psi I apply U to psi and then take the inner product with psi. All I'm saying is I'm taking psi, the old nothing. I apply U to psi. Is this allowed? No, this is not an actual state. But I said, theek hai, chalega. And then I multiply it with this psi itself. Psi itself. They need to see, no? What happened? U times psi, yes. So now what I am doing is, let me write it out. Let me write out this application. You will see that you will have the entire zero vector multiplying with an entire zero vector. This is going to be C1, C2, C3, C4. No, I can't again. Let me multiply this out, which is U times psi is equal to 0, 0, 0, 0 times 0, 0, 0 times C1, C2, C3, C4 is going to give me just a 0. Similarly, 0, 0, 0 times that is going to give me 0. Here I have a 1. So 0, 0 with C1, C2 make it 0, C3 I get. And again 0, 0. So what I have now is U times psi. Maybe I shouldn't call this U. I'll call this M. Let this matrix be M. M times psi gives me 0, 0, C3, 0. And what I wanted to do was to take the inner product between psi and U psi. That is, I write it down again. I have C1 star, which comes from this, times the first element of this, which is 0, plus C2 star times 0, plus C3 star C3, because it has a C3, and the 0. C4 times C4 star times. So effectively, you see that I can drop this out. These are all zeros. So the inner product is just C3 star C3. C3 star C3 is equal to mod C3. Well, this is just complex number things. So now what we said is that if I take this kind of matrix, apply it to psi, this is not a dynamics operation. This is not a unity, so I can't do that. I apply it to some psi. Then I'm picking out just one number. That is, wherever this one is, that corresponding thing, I pick out that number, and then I put it over. Whatever resulting matrix I have, I take an inner product with the initial matrix. What I get is the third number. The third, rather the mod third number square. So now I can create a set of M's. Let me create, I just represent these kind of matrices where everything is 0 except for the diagonal, and everything on the diagonal except for the mth row column value is 1. Everything else is 0. This is what I have taken. I will represent them in the following way. The set of M's, the set of all I said is I can take 1 0 0 0 0 1 0 0 0 0 0 1 so on so on. I take this set of matrices and I associate with every such matrix a single number. That number is Cm. So now I associate with every such matrix PM. Maybe I should call it CM. Okay, fine, I'll just call it PM. I will call it PM. Till now, everything I'm doing is ad hoc. I'm saying, let me define such a matrix, which makes no sense. Let me define such a number. And this number PM equal to M psi, the inner product of psi with M psi, what we had just calculated. I define PM as this, which we had previously seen is equal to CM and square. Does this make sense? No. Yes, no.
Yeah.
Are you sure? Because it doesn't look like it's there. You can ask, it's just I didn't understand what part you didn't get. So
This is not, we're gonna make things more clear now. You're just saying that instead of defining this, you define it as a inner product of phi and phi.
instead of defining what? Oh no, I'm just saying that I've not said in my slides, I've not made it out very clear. I'm explaining what I've written on the slides. That's so it's not complete. Slides are not complete. But all I'm saying is I can define such matrices. That's not difficult to define the matrix. That's fine. Where I define this kind of, this represents a matrix where the mth value is 1. Everything else is 0. Psi m, PM, right, is the inner product of psi with m psi. Psi is different. Yeah. So if you want, you can call it a function, which is Cm square, where C is the component, the mth component of the psi vector. Any other questions? No. Okay. Yes. But now you see that these PMs, if I take a sum over PMs, this sum has to be 1. Why does the sum of PMs have to be 1? Because the sum of mod Cm square summed over M's was 1. We had taken that over here specifically. And because we had taken that over there specifically, PMs also sum up to 1. Now the nice thing about a sequence of numbers that sum up to 1, not a sequence of numbers, but a set of numbers that sum up to 1, is that they can be thought of as a probability distribution. Effectively, what I'm saying is that this M is the probability of measuring the state, this capital M, or rather PM, is the probability of measuring the state in the M state. Does that make sense? Yes, no? Yes. PM, you see that the sum of PMs is 1. That's because the sum of Cm mod Cm square, sum over M is equal to 1. We had taken that specifically. So in the state. So now what I'm saying is that PM is a set of real numbers which all add up to 1. And I am calling this a probability distribution. And the way that I give meaning to what this probability distribution is the probability that your state psi, the state psi, when I measure it, gives me a value of I. The PM is the probability that psi PM is the probability that my psi gives an output of M, which is, if I again go back to my previous example of particles on a 1D chain where you have discrete points on tiles, then the probability that the particle you see is on the mth location is PM. And PM was defined as, not defined, rather we found it. So we Cm mod Cm square. This makes sense. Everyone is fine. Now, because PM sums to 1, what I'm saying is that the probability of finding your particle somewhere on the entire space is 1. That's not surprising. We know that the particle exists. Right. So now to go back and give meaning to the state vector, which we had previously defined as psi is equal to P1 plus C5. So what I'm saying is this gives the meaning of this vector is that Ci mod Ci square is the probability that you will get it in the ith state. On measuring, I get it on the ith state. Now you see there is a clear departure from previous cases. Here I didn't say that anything happens to the system. I'm just saying that okay, I have a system and then I will there's this one singular system and the system has some measurement of x or something like that. Where I can find where the position is. I can know for a fact where this position is, and I can pick x out. I can write down x. Whereas in this case, I went to a probability distribution where I said that one particle, not one particle, rather an ensemble of particles, that is many particles, can come from different places. That is also not surprising. But here the jump that I did was that a single particle results in when I look at it or when I measure it, and the way that I measure is what I told you, gives me a probability of I with a gives me the output I with a probability of Ci square, mod Ci square. But we've still not talked about what happens to the particle after I have measured. So what I said was the probability of measuring it on the ith state is some m. The probability of measuring it on the mth state is Pm, which is defined that way. And what I take the resulting state to be is m times psi. We had previously seen that doing m times psi will give you a set of 0, 0. Let me write it down. 0, 0, C3, 0. This is what it gives. But this is not a normalized vector because C3 itself is not, mod C3 is not 1. It need not be 1. It can, but it need not be 1. So what I do is I will scale it by C3. So this can be more conveniently written down as a measurement. Now also matter of if I measure a system's psi, then it becomes the state m times psi divided by n product of psi. This because this is equal to mod Cm square. This is equal to this kind of vector where these are all zeros and only this is out. No, that is right. Yeah, this. Sorry for the things. So this, if I apply, we have previously said, gives you just a single value with 1 in whatever m. But you previously, as we had defined, the m set, and it is that on scale, is a set of such matrices. Not one matrix, it's a set of such matrices. And the probability of one of these matrices being applied, the matrix that's being applied comes with the probability of Pm. Does that make sense?
Is define PM as probability linear cancellation.
Yeah.
Then you jump that it will be CI mod square.
CM.
How is showing that to be elegant?
Yeah. So M is a very specific kind of matrix which just picks out that value. Correct? PM was defined as psi and psi. This, yes. So, but M psi was just this kind of a vector. Zeros everywhere except for C3 or CM in this case. When I take all the values and then take the pairwise, the way that we had defined the inner product, you go so these zeros will take out those zeros. The only thing that's left is a C3 star. C3 star times C3 is mod C3 square, which is what I defined as PM. And that is what you get here. This is mod C3 square. Because I'm taking a square root, it becomes mod C3. And this is M CM, sorry. M when I'm applying to this is just going to give you 0, 0, 0 everywhere except a CM in the appropriate location. So now you see that you have the 0, 0, 0, this, which is equivalent of writing there's a global phase which
So basically, what we are saying is that when we apply that this population with this predictive measurement and we get the probability of system being in M-state.
correct.
But then we are making it.
No, I'm sorry. What I mean to say is that when you do a measurement, physically, that means that I have this system, I have this quantum system, I make it interact with some sort of a meter, and the actual interactions don't really matter, which is something that's of active research anyways. But and then this meter shows me one value. It shows me a value M with a probability of PM. And the operation in quotes that I'm applying is this. So I have a set of M's and the meter picks out one of these M's according to the probability PM and then applies it like this. This is very different from the normal dynamics that was there where you just had to multiply. There's an additional square root and stuff like that. There's a lot of study of why these extra things are coming, but we leave that for later. 1 hour. Sorry?
Experimentally, it goes in another way. When we are doing mathematics, we are applying this to get probability. But when we are doing experiment, this the system behaves in such a way when we are measuring it, the result of this measurement with the probability.
Correct. And what is the probability? This. That's it. The probability of this being the output vector, 0, 0, 1, 0 being the output vector, is PM, the way that we have defined PM. Is that fine? Is that fine? Do I need to do tensor products? Yes, I need to do tensor products. Do we take a break? Okay, so let's take a 10-15 minute break, or maybe a 5-10 minute break because we started a bit late. And then we'll. Yes, quiet down. Yeah, so let's continue. So just to revise, we have taken a set of states, a set of dynamics, some rules on the states, some rules on the dynamics, and a protocol for measurement. So interesting thing that came up is that the way that I defined these was very axiomatic. I never said why any of this is. So the way that I like to look at physics is something like this, which is why the title of the talk is like that. All of this is effectively axiomatic. Nothing tells me that this is how nature actually works. It's just that this is how I represent nature. The fact that this works out is good for me. I mean, that's why I'm using it. But there's nothing, this is not at least the way I like to look at it, people disagree, this is philosophy. But the way that I like to look at it is that these axioms are not the truth. They're just good enough that we haven't proven them wrong yet. So coming to the next thing is to look at multiple particles. So I just mentioned this, but maybe I should put out a multiple particles case. So in the multiple particles in the classical mechanics, which is with just real numbers, is you just take the Cartesian product. So you take x comma p cos b x1. It just means that I can take now tuples of tuples, and then, like we said, the dynamics depend on this tuple of tuples. Fine. Whereas in the quantum mechanics case, there is something much more interesting that we need to do. I understand why you said it's not just a question now, but I will choose to ignore it still. So now, very similar to the previous case, let psi be the state of one system and phi be the state of another system. These are two different systems. These are two different particles, not the same particle, two different particles. I take psi and phi, and I want to now represent the system composed of phi and psi. That is this, let me call this particle A and particle B. So I want to talk about the system that is composed of particle A and particle B. And I want to talk about the state of this, because at the end of the day, I still need to do this again. So what I call the state is, I will represent it with this. I will represent psi and phi with this kind of a notation. This is still just notational. There's nothing, I'm not introduced what this actually is. What for current cases, we will go ahead and we will say that this is how I define a state, and the set of numbers that we previously had of, let's say, C1, C2, dot dot dot. So the way that you do a tensor product is taking C1, C2, dot dot dot, D1, D2. But I take C1 times C1 D1, C1 D2, dot dot dot, C1 Dn, then C2 D1, dot dot dot, C and Dn. This is how I write down this new vector of the system together. And this is how I call, this is what I call taking a tensor product. All I'm doing is I'm taking the first element of this, multiplying it with D1 and D2 and D3, putting them one below the other. Then under that, I take C2, D1, C2, D2, so on and so forth, under each other, until I have a long list of an n square length of vector, or rather nm. But now we talk about what kind of dynamics we are allowed to apply rather. One kind of dynamics that you are allowed to apply is, now first things first, once I do this long business, I take this entire length thing where when I do the tensor product and get this long vector, this is now a quantum state. And therefore you can show again that if this is normalized, that is, if the sum of the mod square of the components is 1 and the same for this, then the resulting one is also 1. You can show that by hand. It's not very difficult again. The next thing that I wanted. So now we have this as a quantum state, which follows this kind of system. It's just now instead of D, it becomes D square. And now I want to look at the dynamics that is allowed on this. Now, one kind of dynamics is where I say that system A evolves separately with unitary U1 and system B evolves separately with unitary U2. There is no interaction between these two, right? And in such a case, I can represent the resulting operation as U1 tensor U2. Again, U1 tensor U2, you can look up the way that you write the tensor, but effectively all I'm doing is U1. If I take this and then I apply it to psi1 tensor psi2. So am I going off? Yeah. So I'm just dropping the tensor sign for now, where I can. There is a tensor sign over here, I've just dropped it. And multiplying this matrix with this, it is equivalent to doing U1 times psi. Psi tensored with U2 times that is, if I have an operation, if the dynamics is such that psi evolves separately or A evolves separately and B evolves separately with U1 and U2, then or UA and UB, then I can simply talk about how psi evolves with this U1 and how phi evolves with U2, and those we know how they are, and then I can join them back. So and this is a very special kind of operation where you have these two particles which are non-interactive. They don't influence each other because you see that the evolution of psi is completely independent of phi, and the evolution of phi is completely independent of psi. It's just completely determined by its internal dynamics. But it's rare that you get such kind of systems. You tend to only approximate them to such kind of systems. But when you don't have it, then the more general case is where you have, again, you have the state. There was nothing new about it. We just took a bigger state now. And therefore, your unitaries now have to be bigger, but they still must follow this kind of structure. So that is the more general evolution, but quite often you get these kind of evolutions are pretty common also, especially in quantum computing, where you have single qubit or double qubit gates. You don't have to worry about more than that. So this is what we'll deal with. This is still pretty abstract. We'll come to more specialization in this thing. Now the final step is of measurement. I should have probably added one more column, but I don't have space. Is of measurement, but measurement becomes problematic because it's not problematic really. It's just, it again takes a little bit more carefulness, where, like I said before, I have this set of M's and PM's and all of this, but it's on for each of the states, for each of the systems. That is, for A, you have a set of M's, for B, you have a set of M's. And the application and TM and everything depends on those two. So now what happens is that if I have such a kind of state, still skipping over the fact that these are product states, but I'm hoping Aabhas does it tomorrow. Then if I take, let's say, psi, yes, and psi is C1, 1, C2, 2, so on. If I apply this M on it with a probability of PM, I will get, or not on it, I'm just applying it on this first system. I only measured system A. Then my resulting state will be this with a probability of PM PM psi was defined as before. This, the inner product of psi with M. So now what we are doing is we are only applying M on the first one. But because this is a much longer vector and this is a smaller vector, we need to make this vector bigger. So all I do is I take, let me use this. I take M tensored with identity. The identity matrix you know. So again, this is homework question. You take M as defined before, which is the mth element is 1, everything else is 0. Tensor it with the identity. Check online how to do the tensor product and then apply it to such a state. Then you will see that you will pick out just that PM psi with M tensored with this. So now we had previously said, now I'm going to erase the whole thing. Now let us consider a specific case where previously I had said that this could be C to the power D, which is the states can have multiple such components. Now I'll reduce the number of components to just 2. The reason why I'm doing it is simply because 2-level systems are very simple. They are the simplest I can get without absolutely losing out on everything. For example, if I just have a 1-level system, one second. Yeah, for example, if I just have a 1-level system, then all I have is C1 times 1. But mod C1 square must be 1. So all you have, the only kind of number that you're allowed is e to the power I5, but then e to the power I5 goes off. So this doesn't really matter. And the only state effectively you can have is 1. You can't have any sort of evolution because the only kind of evolution you can have are the trivial evolution of nothing happens. And the only measurement you can get is 1 with a probability of 1. So there's nothing. This is literally a pointless state. It's a trivial state. There's nothing in it. So the minimum you need to have is two levels. And simply because we come from, just a second. The simplest case is of 2. So I'll take 0 plus 1 and call them 0 and 1, and previously C0 and C1. C0 and C1 are real numbers. But because C0 and C1 are real numbers, sorry, not real numbers, complex numbers, I can write them as R0 e to the power I0 into that. R1 e to the power I5. This is just the polar notation of complex numbers. But we have an additional constraint that C0 plus mod C0 square plus mod C1 square is 1. So therefore, all I'm going to say is R0 square plus R1 square. When I take the mod, this e to the power I5 goes out, and you just have this is equal to 1. Equivalently, R1 is just 1 minus R0. But more importantly, because R1 and R0 are real numbers, I can write R0 and R1 as cos theta and square plus sin theta square for some theta. You can, I mean, the fact that you can write R0 square plus R1 square as some cos theta plus the same theta sin theta square is something that you would have done multiple times. So what I'm going to do now is I'm going to replace R0 with cos theta and R1 with sin theta. Okay. Now the next step that I'll do is I will divide the entire thing, divide and multiply the entire thing with e to the power I phi naught. So this becomes phi 1 minus phi 0 cos theta plus this, the whole thing times e to the power I phi. Right? All I've done is I've taken e to the power I phi naught root. Nothing special. But you will see that given any side, again, this is homework, I guess. Given any side, I take the measurement of this and I take e to the power I phi side. And I take the measurement of this, the measurement statistic. So calculate PM for any side. Take any side, calculate the PM, that's not very difficult. Take e to the power I phi for the same times the same side and calculate the measurement probabilities for that. You'll see that they're the same. It's very easy to see it when you literally write it down. These are constants, they can come out. Then, but because you need to take a complex conjugate, this goes on. Which means that I can, for every state e to the power I phi times psi, I can simply write it as psi. A global phase does not matter. You will eventually realize, hopefully in tomorrow's talk, that this global phase does not even exist. It's just that it looks like it exists, but it's not there. Which is what I am going to do now. I am going to say that let me drop e to the power I phi naught. Because I said that the measurement statistics are the same, which means that whatever I do, I cannot differentiate these two states. If I cannot differentiate these two states, they are the same state. There's nothing, again, this is a bit philosophical, but I can replace this. And I can just write it as cos theta. Sin theta and theta 1, phi 1 minus phi naught. I will replace it with a single value phi. So I have a real the component of 0 is real and the component of 1 is not real and it's complex, but it has a very specific form of sin theta times this. So now this is a very interesting thing because I can represent every two level state with just two real numbers, that is theta and phi. If I give you theta and phi with their limits, theta goes from 0 to pi and phi goes from 0 to 2 pi. I think. Yeah. I give you these two things, theta and phi, then just these two values can represent the entire system. So what we previously said was actually two complex numbers is actually just a state of two real numbers because of two constraints. One is the constraint of the norm being equal to 1, that drops one of the real numbers, and the other being the fact that global phase doesn't matter. Both of these will drop two of the freedoms in your degrees of freedom, giving you only 2 degrees of freedom, which is this theta and phi. Now, because theta and phi are with the same range, I can add another number, r, which is equal to 1. This is the equation of a sphere of radius 1 in polar coordinates, where theta ranges from 0 to pi and phi ranges from 0 to 2 pi. I have a sphere, which means that every state, theta phi, can be represented and it's outwards. So you have this and you have a sphere, which is obviously a circle. And I can represent every theta phi as the normal polar rotations of an angle of phi from the z-axis and an angle of theta from the x-axis on the x-axis. So I can represent some vector like this. Therefore, what I can do is I can represent all quantum states of two-level systems and only two-level systems on a sphere as points on the sphere, not inside the sphere, just on the surface of the sphere. And I call this sphere the block sphere, simply because the first person to look at this was dude by the name of Bloch. Now we can look at unitaries, going back to that same table. What is a unitary? A unitary is just a rotation, because if my initial state is a point on a sphere and your final state is a point on a sphere, then I can find a rotation which takes you from there to there. And because unitaries take you from states to states, all unitaries must be rotations. Equivalently, a rotation is something that retains the length of your vector, and which is what we previously defined it as, that U dagger is identity. So a little more than that, you can also look at U dagger as the reverse rotation. So you rotate it forward and then you rotate it back, it should give you an identity. There are three kinds of rotation, I mean, not three rotations, but you can define any rotation on a sphere with just three rotations: a rotation along the X, a rotation along the Y, and a rotation along the Z. Technically, you just need two of them, but finally, you have, right? Because you have these three kinds of rotations, there are corresponding three operators: the Sx, or the sigma X, the sigma Y, and the sigma Z. The exact representation sigma Z is equal to 1, 0, 0, minus 1. Sy, sorry, Sx, it's 0, 1, 1, 0. I think so. Yes, yes. And Sy is something else, please. No one thought about it. Right. So these are two operations which I can apply on a state which looks like this, and I will get new states. The Sx, if you apply it, you will see that it is a rotation of 90 degrees about the x-axis. That is, if this is the x-axis, I go from here to here. So if I take a state of cos sin I phi, so I take cos theta, sin theta, and this called sin theta, and this referred to as s of theta, e to the power I phi. And I multiplied with Sx. Rather, I multiplied here. Sx times this is, if you just do it, you multiply 0 times 1 time of this, which gives you 0 times cos theta, 0 sin theta. So you get sin theta e to the power I phi, and 1 0 multiplied with this gives you cos theta. So effectively, what you have done is you flipped it up. So the component that was along the 0, which is in the up direction, is now the component along the negative 1 direction.
So, like, why do you consider them to be rotation for reflection? Is there any point of considering them to be?
All reflections are rotations.
Oh, okay. Is there any point of reflection?
Yeah, because I can talk about not a 180 degree, but rather just a 90 degree thing.
No, what is the significance of it being there?
Yeah, the fact that it retains 1. But that's my point, right? All reflections are rotations, but not all rotations are reflections. So therefore, I can call them rotations, and therefore, yeah, I've also taken care of reflections. Yeah, some of them look like.
Say it again, why they are rotation, why?
Yeah, so if I have a point on a sphere and I take another point on a sphere, I can always go from this point to this point along one great circle. So they're called great circles in geography, but that is just a rotation, right? So I can just find the ring that joins these 2 points, take the axis, and it's just a rotation about that ring. Or I can take one rotation like this, go around, take another rotation. I can compose rotations, and then that forms a group. It's called SO3. But that's not how. But yes. So you have these Sx, Xy, Sy, and Sz, which are the discrete versions of rotations along the X, Y, and Z, which is I'm only allowing it a pi shift, that is, I'm reflecting it along x, y, z. Anna said. But I can also have the infinitesimal one where I just rotate it a little bit by an angle of a small angle of alpha. And I can compose them to get 2 alpha, 3 alpha, and then different directions. And I can compose multiple rotations to get all rotations on the block sphere. However, it's nice to introduce certain half rotations. One is called the H rotation, which is the Hadamard gate, which has this kind of eraser. This one is H, which has the form of 2 by square root 2, 1 by square root 2. I think this is the. Yeah, this looks right. But yeah, this is what it. This is a gate called the Hadamard gate, or it's still just a rotation. It's just a rotation along a weird axis. There are nice animations online. I wanted to show it, but it's so. Now let me apply the Hadamard gate on the 0 state. That is 1. This is that because it's a 1 here plus 0 times 1. So right, and let me apply the Hadamard gate. This, sorry, not equal to H times this takes you, if you do the multiplication, I'm not going to wait for you to do it. Gives you 1 by square root to 1 by square root. Which means it takes something in the 0 state to the this state. Goes from this state to that state. Now, this state, if you look at the measurement statistics of PMs, that as I calculate P0 and P1, it is just mod of this square, which is mod of, because it's a real number, the mod is the number itself, and square of 1 by root 2 is just half, which means that the probability of getting 0 is half, the probability of getting 1 is half. So it goes from a state which had no superposition in it. I don't want to call it. It was a state which gave you 0 all the time on measurement to a state which looks like this. Similarly, you take it with 1 and you can use the Hadamard and you get the same thing. Not the same thing, but this is, I mean, you can apply 1. This is the 1 step on this, and you get a minus. Same thing. Again, you take something which had no superposition in it and put it into an equal superposition state. This is the Hadamard. Similarly, there is something called the T gate, not the Topley gate, if you might come across it. It's just called the square root of X gate or something like that, because it looks like half a rotation along the x-axis. But anyways, let's not get into that. Finally, I mean, till now what we have talked about were all single qubit gates. That is, I had one particle which existed on this block sphere and it rotated up. Very nice. But clearly, like we said before, that the dynamics of systems cannot be completely defined by the individual dynamics of each of them. That is, I cannot take U1 tensor U2 and then say that U1 tensor U2 is the resulting operation. There must be interactions between these. So till now, all I have introduced are single system operations. Now let me introduce one multi-system operation. Yes.
Like, if there has anyone found, like, you have a representation for a two-layer system. So, is there no representation of the multi-layer system, or is it two forms?
What do you mean? No representation? You mean in a block as a block sphere equivalent for qubits. So the thing is that the surface that a qubit gives you is not easy to define. You can take sections of it which look like spheres or certain nice features, but there's no one thing that defines it. But it's still unitaries are still rotations, but they're more generalized rotations in higher dimensions.
That on the SOM or some other general.
I'm not sure. But there is a paper by Sandeep Goyal if you want. But effectively, what they proved, I mean, it was pretty well known. It's not just that, oh, we went from, for 2-level systems, we had a 3-dimensional sphere. So a 3-dimensional system, you have a 4-dimensional. No, that's not the case. It's more complex than the manifold or the surface that the points lie on are more complex than that. So you can't just imagine them as a sphere and over rotations. They are still rotations. It's just a more generalized rotation. It's not the rotation that we think of. That's all. C naughts, yes, C naughts. So I defined the C naught on 2 qubits. Previously, I had just 1 qubit, 2 qubits. Previously, I said 2 qubits have 2 levels. 1 qubit has 2 levels, but 2 qubits then has 4 levels. So 0, 0 level, 0, 1, 1, 0, 1, 1. See, now you see why very conveniently we are moving towards computation, where all of this look like physics until I write it down as 0, 0, 0, 1, 1, 0, 1, 1, and you're like, oh, bye. And now I'm representing things as binary numbers, as states that the quantum system can take. And I'm saying, oh, I can do computation with it. But all I'm doing is physics. And equivalently, when I'm doing physics, I can say, no, all I'm doing is computation. They're not very different. It's just how you look at things, what questions you ask that are different. So the C naught is a kind of gate which looks like this. This is what the gate looks like. These big zeros are just zeros. Now let me apply the C naught on this gate. Tensor with the theta phi state is just cos theta plus I e to the power I phi sin theta. That's all. I'm just representing it. Let me apply the C naught on this. Right. The resulting state. Let me write out the resulting state is cos theta 0, 0. E to the power I phi sin theta 0, 1 plus. Why? Because I'm taking 0 with the 0, that is 0, 0, 0 with the 1, 0, 1, putting the correct components. Nothing fancy. Right? Now let me apply this C naught on this. Let me also write this as a vector. This as a vector is 0, sorry. Cos theta. Now I take this, apply it to this. I will not let, I'll let you do it at home. You will see that on application of the C naught, it remains as is. Cos theta I e to the power I and 0, 0. You see that there's no change. However, what I'll do is I will replace this 0 with a 1. Then this becomes a 1. This becomes a 1. This becomes 0, 0, C theta, e to the power I phi sin theta. Sin theta. this becomes this becomes 0, 0, e to the power I theta sine theta. Oh, sorry, e to the power I phi is theta cos theta. This is what this looks like, where all I've done is I've switched these. So effectively what I'm saying is that, let me write out this. Okay, let me not. Right, so what I'm saying is, if the first qubit is in 0, then it is as if nothing happens. If the first qubit was a 1, then it looks like it switches the second part. So what I'm doing is I'm saying, if qubit 1 is equal to 0, then qubit 2 is as this. Q2 is equal to 2. If Q1 is equal to 1, this is Q1 is equal to 1, then Q2 is equal to not Q2. That is, I'm rewriting this. So you see what I'm kind of doing is a if condition, where I'm saying if Q1 is 0, then don't do anything. If Q1 is 1, then do something. That is, do a lot. This is a controlled operation. Controlled on Q1, I am doing something to Q2. Now I can rewrite the C0 in the opposite direction also. Just put this block here, and now I'll have a control on Q2. That is, if Q2 is 0, then do something to, don't do anything. If Q2 is 1, then do something to Q1.
Where are you applying C0? You get the tensor product of the 0 and theta and phi. Then you are applying C0 to the entire tensor product.
Because C0 is the operator that operates on 2 qubits. It can't work on 1 qubit. It needs 2 qubits. Clearly, I can't multiply this with 2 numbers. I need 4 numbers.
Defining C0 originally as just these 4 states. Now that's
C0 is not a 4 states. C0 is this matrix.
But the original wrote down C0 as 0, 0, 1,
0, 1, 0. Then this is C0. And then I'm applying C0 on a state, looking at what happens. I can go the other way, saying that I want a operation that does this. We should have introduced it this time. So I want a gate which does this. I then say this is the gate. I can then show it by just applying those operations and it. This is what C0 is doing. It's saying that if it is 0, leave whatever it is. But if it is 1, then flip that. And this operation can be represented by this. I say that's my hypothesis, and then I just show that it works. That's enough. But also, I mean, given the fact that these are linear things and this is a unitary, you can write down 0, 0 going to 0, 0 is this vector. This is this vector. Then you flip it also. But you can write it that way, but
you can just come up with any matrix which let you to come one thing to another.
yes, as far as that matrix is unitary, it's allowed. It's a whole different deal whether you can implement that on a computer, which is next talk. But yes, like you said, any unitary is allowed. Any matrix such that it satisfies the unitarity condition is allowed. Currently, then tomorrow Aabhas will come and say, no, there are more such matrices which are more, they're not matrices, more operations are allowed, which are more general than this. But for quantum computation, this much is allowed. Great. So we have defined the C naught. I'm going a bit too slow. So now I can do one thing after another thing. That is not very surprising. I can apply a rotation in the X, then along the Z. Therefore, that is called a serial composition of gates. So if I have a state psi, I can first apply CSZ to get some psi prime. Then apply SX to get some psi double prime. I can do this, which is basically one after the other. I am putting operations, which is exactly what we do in programming also, where you apply one gate after another gate. But physically, this just means that first one set of dynamics happens, then I change something such that another set of dynamics happens. It's nothing fancy. But I can also have parallel composition, which means that if I have two states, 5, then along with SZ, I also apply something like H, let's say. These can be any gates, I'm just saying that. Right? And stuff like that. So you can have serial composition one after the other, parallel composition where I apply gate on one qubit and the other qubit and the other qubit at the same time, which comes to the problem of circuit depth, which is given a sequence of gates, what is the least amount of time that I need to apply it? One good question is consider the following circuit. I am kind of skipping over the definition of circuits. It should be pretty clear. Is it that this is one qubit, this is the other qubit, this is the third qubit, and you're doing things.
So how are you making them like physically parallel?
Next. What?
Okay, serial composition is fine. This is a system you do some measurement, then another measurement. How do you
I'm not doing measurements. I'm talking about units. I'm not yet reached.
how do you do this in parallel composition?
Parallel composition simply means that I have one box here, one box here, one box here, 3 qubits. I can apply a box on one and another at the same time. So now let's look at this circuit. This is just a C naught, where this is the control qubit and this is the knotted qubit. And so now I ask you, what is the depth of this circuit? That is, what is the minimum amount of time that I need to wait such that this circuit completes? One way of doing it would be to apply this gate first. So I take one step, this gate another, one step, this gate, and then this gate. It's a total of 4 steps, time steps. But I'm allowed to do parallel composition, which means I don't have to wait for one thing to end to start the other. So what I can do is I can pull this box back. I put them together. And this box over here. Which means I can do these 3 parallel and these 2. I mean, this needs to happen at another step. But let's say I had a box over here. Say I had a box over here. I can't pull this behind because it depends on this first. So therefore, even though this is just waiting blank for this time step, I can't put anything because the first step requires a previous composition, But there might be certain gates where you can reorder. Reordering is instead of saying that I do A followed by B, instead of doing this, I'll do B followed by A. This should be allowed. I mean, in some cases it might be allowed. These matrices, nothing special, are called commuting matrices because AB is equal to BA. Sometimes you can reorder things. sometimes an application of A, B, C might be equal to B, C, D or D, E, F, where I can reorder them in such a way that I get the minimum circuit depth. Why do I care about circuit depth? Well, because I want things to be fast. I don't want to wait too long. I want them to happen quickly. And this is an entire concept of circuit compilation of what is the right way of applying my gates so that I can get my state. So one nice question
Yes,
is
the original concept of circuit depth, it has to return to the same state.
no, not the same state. You want it to go from some state, from some initial state to the result. I mean, you want a target state. You want it to reach something so that you can gain information from that. But you don't want it to go back to its initial state. No, because if it goes back, then you might as well not do anything. It's right there. You don't want to do it. The fact that it's reversible means that I can undo it, but we are not getting into that. Cool. So now what I have shown you, everything I've shown you on the board, very clearly, I've demonstrated that I can do everything on the board. I can do it by hand. If I can do it by hand, I can code it onto a computer and a computer can do it also. Therefore, why do I need quantum computers? There's no reason for quantum computers because I can do everything by myself. The point is that quantum computers are very good at doing simulating these unitaries. These unitaries, which I'm applying to quantum states, they can do it much faster than a classical computer can. And therefore, because my entire circuit is built up of these unitaries, I would rather use a quantum computer to do it.
So what do you mean by do it fast?
So this on a classical computer, this matrix multiplication requires n square multiplications and n additions, right? Because I'm taking this with this, this with this with this, so on and so forth. So you'll have n square of those multiplications, and then you have to add up each of the rows, so you get n additions. But this effect, I mean, there are much faster ways to do it, obviously, because it has more structure than random matrices. But effectively, this is the amount of time it takes for a classical computer to do this multiplication. However, for a quantum computer, because the quantum computer itself is like this, I am representing the quantum computer itself. Applying this gate is a single step process. So this entire gate that I did takes a fixed amount of time. It's not zero, though we'd like to think that it is, a fixed amount of time. We don't really care about how much time it takes, but not all gates take the same time. Some gates take a little longer depending on the way that the system is built, which is what the next thing is. But for the abstract definition of a quantum computer, these gates just. The game then is to build the correct kind of unity. So probably one of the first algorithms which gained lots of popularity for showing the quantum supremacy is the Dhruva search. So I guess we'll end with that algorithm. So we'll start off with the linear search on an unstructured database. So suppose I give you a piece of paper with names in a random order. I give it to you and say, check whether the name Dhruva is in this list. If it is ordered, you can just, go to the D and then say, okay, in D, go to the H, and you can just look at that. Or even if you don't know where the index, if you don't know the index, you can go to the first name that starts with the name. Go to the last name that starts with a Z. Clearly, it must be between these two. So let's go in the middle. And then I say, oh, this is somewhere, let's say an N. So then it must be between A to N. So let me go there. Let me break it up. This is very similar to how we play the game of I guess a number and then you tell me, you keep guessing numbers and I tell you whether it's higher than that number or lower than that number. And the optimal guess strategy would always to be guess the midpoint. That is, if let's say Arnav is thinking of a number, I guess 50. And he'll say, is it higher than 50 or lower than 50? A number between 1 to 100. And then if it's lower than 50, I will guess 25. Then 12, and then between that and so on. So effectively at each step, I can break it into half. However, if I don't know that they are ordered, for example, I don't know that list is ordered, I can't say, oh, the last one is C, and therefore that cannot, the name Dhruva cannot be in that. I cannot say that because it might be before, because it's not sorted. So the only way then is to literally go through each of the names one after the other to check whether Dhruva exists. Now, let's say Dhruva does not exist. The only way you can be sure that the name Dhruva does not exist in this list is to look at all n of those numbers, not numbers, the names. And that if I double the number of names, then you take double the amount of time. That is the best you can do. But the quantum version of this system, I mean, this problem is, I give you a state, I give you a hidden state. There is some state which of something that looks like sigma and z. Maybe we should take it as sigma. Let's say I take 0. This is a state. This is the selected state. I want to search for this state. Right. I don't want to search for this. I give you a box, a black box, which is a unitary operation, which tells you, which does this thing. It takes any state that you give it x, and it gives you minus x if x is equal to x star, else it just returns x. That is, I take x, if x is the selected state, then I give minus x. If x is not the selected state, I return x itself. So if the selected state is, let's say, 101, then u of 101 is equal to minus 101, whereas u of 110 is equal to 110. That's all. This is the this is the box that's given. This is equivalent of saying that there is a name which is selected, and find whether the name, tell me what, find where this name is effectively. You are given this, and we call this the oracle. The reason is it is modeled after this kind of system where in the game that we were previously playing of guess the number that I was thinking of, Arnav is acting like an oracle. I can ask Arnav only one thing: is this the correct answer or is this the wrong answer? And Arnav says yes or no. Arnav does not give me more information saying how close it is, how far it is. In this case, he just says yes or no. But let's say Arnav decides that no, I can also, Arnav decides that he can tell me whether it's higher or lower. Now I get a little bit more information. But if he just says yes or no, then I have to go through all 100 integers, and only then can I guess that, this is your number. Right. So I devise a protocol, right, where I say, let me take, let's define it on a three qubit system. Define it on a 3 qubit system. Oh. Right. Right. Yeah, I take this step.
And now that the unity which are defined, so it will be specific to that list in unordered list.
Yeah. Not that unordered list.
It is specific to what you want to.
Yeah. So, yeah. Go on. What is it?
Okay, so all you've defined is also just, so you take. See, or like, the only thing you've done now is you've defined a task and you've said that an oracle exists which tells you to restore.
Yeah.
Okay.
And the game is, guess what the oracle's number is. Guess X star, given the oracle only tells you this much. So one way to do it is to give the oracle 0, 1, 2, go through all the way and say, oh, okay, what happens? That's kind of dumb because the oracle allows, because we are dealing with quantum mechanics, the oracle can operate on all of these at the same time. So, parallel computation, right? And let us say for this current this thing that 100 is the selected. This is the oracle's internal state or whatever, and this it gives you a minus sign. After applying the oracle once, I get this, right? And effectively, what we have done is we have applied you have asked the oracle all of the options at once, and you get all the answers together, and that's great. So now a lot of people will say, yeah, this is where the power of quantum computation is, because you are doing you're asking multiple questions all at the same time. You are putting them all into different probability mixture and then putting it through the oracle and it's saying it. But that's not where the power is, because all I'm doing over here is I'm asking all the questions together. How do I extract out this? I still can't. There is still more to be done regarding this operation. So now I will try to show the Dhruva search.
But I don't see how this is different from asking from parallel computation itself.
Yeah. I know. Sorry, that's what I said. That parallel computation is not enough. There's more that I'm doing, which is what I should. Right. So now I will just look at the state instead of writing out the states. I'm just looking at the C value, the component of that state, and I will plot them as instructions. Yeah, this is the square root of it. This is the state that we started off with. After applying the oracle, we take one of these states and we made it negative. Yes. Now what I will do is I will take this line and I will reflect it about this line, which means that this now goes up here, and all of these go here. Yeah. So I had initially there, I applied the oracle, it changed one of them to the negative side, which is, it has a negative component, but the amplitude is negative, but the probability is still the same. I mean, if I take the probability, it still gives the same. So if I measure it after doing that, I have nothing else. But what I do is I will reflect it about this dotted line. This dotted line is the uniform superposition vector, and I reflect it about that plane.
They sort of cancel the.
Yes, so whatever was above came down, whatever was below went down. I mean, I don't think this was a very. Maybe it should have just come.
What about things that were below the line? But.
Yeah, whatever was above the line came below. Whatever was below went
went above.
Yeah.
But they're not in that
They're not in the.
diagram.
That is what happened, right? It was below, it went up. Whatever was above came below. Now I apply the oracle again. Now this goes down. Yeah. The dotted line is, I know, this is more intuitive, but the dotted line is effectively the uniform superposition vector. The uniform superposition would have looked like this, but I've also drawn it like that. But so effectively what I'm doing is I am reflecting about I'm applying the oracle, making it negative, then reflecting it above a line which is above the zero, so that it becomes bigger. The equivalent way of looking at it, maybe this is not the nicest way of looking
Yeah, so okay, we suppose you're dealing with the two-level state. So you have different vectors on the block state itself, and the uniform property vector would just be the summation of all those normalized. That's
Yes.
right. So,
Yeah, I mean, then in the block vector case, it's just this. I start off with this. I mean, if I have just one system,
yeah.
then you have something else. Yeah, you can think of it like that, but there are only two states in a block. What was it? Yeah. So another way of looking at it is, let me look at this. Oh, sorry. I had taken 3, right? No, I have taken 8 systems, yeah. Yeah, I think so. Basically, it's a fully connected graph with 8.
Jump from oracle.
I'm not sure that yet. So let me represent all of this as the state. So this is the 0 0 0 0 0 1 0 1 0 0 1 1 0 1 0 1 0 1 1 1 0 1 1. Right? What I do is that I start off with my what do you call them? The probability district, not the probability, I take it in a superposition of all of these nodes with equal that keeps happening. Oh no, wait, mine. Sorry. Sorry. I take them as equal superpositions, and effectively what I have is 1 by square root of 8 here, 1 by square root of 8 here, so on and so forth. Now I apply the unitary. on this. Effectively, what I'm doing is I'm taking 1, 0, 0, which is my selected node, and make it minus. Now what I do is I apply the diffusion operation, which takes this here, this here, this here. So this here, this here, this here, it goes everywhere. And this wave goes around everywhere. These waves come in everywhere. But this has a negative phase.
Now, could you explain?
Yeah, so I take my probability amplitudes to be 1 by square root of 8 everywhere. Then I apply the oracle, which flips this inverted. Then I apply the diffusion, which basically takes this, divides it up into 7 different parts, sends it everywhere. And similarly, the others also. So what happens is you have a negative wave going out of the selected node and positive waves coming into the selected. Yes. Yes. So all I'm doing is, because there is a negative, there's a negative wave, you have a, because there's a negative wave, you have a destructive interference on your other nodes and only a constructive interference on your selected. Does that make sense? Does that make sense?
No, so if you're describing diffusion using a previous how it works.
I can 2 times. This is what it looks like. It's clearly not very useful. That's why I didn't want to show it that way. It's a reflection about the psi vector. If you look at the reflection about a thing, you can write this as V dagger, V transpose V minus second. This is for normal ray optics, a reflection about a normal V is defined like this. Similarly, I've done the same thing, but it's not very insightful. That is why I chose this. Effectively, what I'm doing is that wherever there is the answer, the oracle, it puts it into superposition so that, it puts it into a negative phase so that there is destructive interference elsewhere. And this game of putting interference, of using interference to increase the amplitude in the correct answer node is the game of quantum computing, is one of the games of quantum computing, where you use interference, which you are allowed to do because these are complex numbers. If they were real numbers, I can't put it negative. This would not be allowed.
So, so if we had, let's say, so how would we honestly reflect a state?
Yeah, okay. So I'll take questions later. Let me finish it off. Sorry, I know, but so the Grover search is one such place where, I mean, it's almost done. The Grover search is one such place where you're smartly introducing interference between correct answers and wrong answers, while also checking all answers at the same time. So the parallelism is what the parallelism that you talked of, where I'm checking all answers at the same time, is not enough. I also need to make sure that the correct answers interfere with the wrong answers in such a way that the wrong answers all get cancelled out and only the correct answers remain. With that, I'd like to end it. Yes. Yeah, there are 4 people on here, but does anyone have questions? Zoom. It doesn't look like, yeah, you go on.
I didn't quite.
Sorry, but go on. Huh?
So, like, the one which has negative phase, it got a different in all the other.
All the other nodes, yes.
So how are all the other nodes affected by the other nodes?
Nothing happens. I mean, there's constructive interference there. But if I take 1/7 of this, put it here, and then 7 other 1/7s come in here, nothing happens, right? So if I don't apply the oracle, this remains as is.
Yeah, okay.
Nothing is happening. But because the oracle puts this into the negative phase, and I'm allowed to put it into the negative phase only because I'm allowed to use complex numbers. Whereas if I had them as real numbers, which would be a probabilistic ensemble, then I wouldn't be allowed to do this. And if I'm not allowed to do this, then this will remain positive and I have nothing. And the only way then would be to check each of them, sample it one after the other, see if there's an answer. The game is to get an interference in such a way that everywhere else there's negative interference, but there's positive interference.
And that is the application of line.
Yes, this is just diffusion, but this is where the interference part comes. As in, this is what introduces the interference. Yes, any other questions?
So if it's probably a problem, mentioning things like unitary algorithm, which is the special case where both evolve separately.
Wait, I'll just. Thanks, guys.
Okay, so we will come back at 3 and Sahil and Apraman will be talking about more experimental aspects and more applications of whatever we have discussed so far in quantum computers mostly. So we'll be back at 3.
Yeah, okay.